Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to provide an overview of causal inference. Previously, we explained when observed statistics such as conditional probabilities, conditional averages, correlations, or linear regression coefficients reflect causal effects. We did this right after introducing each of these quantities because I believe that it is very important to emphasize that they in fact may not capture causality. However, it is also useful to consider all of them together because the same guiding principles determine whether we can use these statistics to perform causal inference. That's exactly what we're going to do in this video. We're going to focus on the common principles and give an overview. If you want more details about how to use each of the individual statistics for causal inference, you can take a look at the individual videos or at the book. Let's get to it. We're going to give an overview of causal inference, and the key question that we're considering is, when does an observed statistical effect imply a causal effect? We're going to use 4 running examples to explore this question, and I'm going to introduce them. In the first example, we have a new drug that we want to evaluate, and we give the drug to a group of people that we call the treatment group, and we do not give it, we give them a placebo, to another group that we call the control group. Some of these people recover. These are the happy blue faces, and some of them do not recover. Those are the sad red faces. 25% of the people in the control group recover, and 75%, 3 times more, of the people in the treatment group recover. So it may seem that the medicine is working, but we will see that that is not necessarily the case. The question that we're after is whether a new patient is more likely to recover if we give them the medicine. The second example that we're going to consider are NBA players shooting three-pointers. So this is the three-point percentage over the 2015 season, I believe, for Stephen Curry and for Courtney Lee. And we see that Courtney Lee made more his three-point percentage is higher, 43.9%, higher than Stephen Curry's. So here the question is, does that mean that Lee was a better three-point shooter than Stephen Curry? In case you don't follow basketball, that would be a pretty surprising statement, given that Stephen Curry is widely considered to be the best three-point shooter in history, and this is from the season where he obtained the award for the most valuable player in the NBA precisely because of his three-point shooting. So we will see what is going on here. The third example are grades in a Portuguese school where some students receive private classes, and those students have an average grade of 10.94 over 20, and other students do not receive private classes, and those have a lower average grade of just 9.98 over 20. Here the question is, are these classes useful? Finally, our last example tries to connect unemployment and temperature in Spain. In this scatter plot, you see the temperature in degrees Fahrenheit in different months in the period 2015 to 2022, and the corresponding unemployment in millions. And we observe a correlation coefficient of minus 0.21, which indicates a negative correlation between unemployment and temperature. When it's warmer, the unemployment goes down in Spain. And now the key question is, would an increase in temperature decrease unemployment? Where even not knowing much about economics, like I don't, this seems pretty surprising. So here the plan is going to be to introduce the framework of potential outcomes that enables us to ask these causal inference questions in a more rigorous way. Then we're going to talk about confounding factors, and finally we will explain how to adjust or control for these confounders or confounding factors. So let's begin with potential outcomes. We're going to do probabilistic modeling of causal inference where we're interested in an outcome Y. Here, outcome does not have the same meaning as when we're talking about probability spaces. The outcome is just a random variable that represents the quantity that we're interested in. And there's going to be a treatment T, which in the case of the medicine, for example, is whether we give the drug or not. and we want to determine whether there is a causal effect of the treatment on the outcome. In the case of the drug, as I just said, the outcome is whether the patients recover or not. If y is equal to 1, the patient recovered. If y is equal to 0, then the patient did not recover. And the treatment is whether they received the drug or not. If they received the drug, then they're in the treatment group. And if they did not receive the drug, t equals 0, they are in the control group. Now we can interpret the statistics that I mentioned earlier in terms of y and t. 0.25, which is the fraction of patients that recovered in the control group, is the probability that y is equal to 1, the conditional probability that y is equal to 1, given that t is 0. The fraction of patients that recover in the treatment group is the probability that the outcome is equal to 1 when the treatment is equal to 1. And now, later on we will discuss whether these conditional probabilities reflect a causal effect of the treatment on the outcome. In the case of 3-point shooting, the outcome is whether each 3-point shot goes into the basket or not. If it goes in, y is equal to 1. If not, y is equal to 0. And the treatment is the player who shoots. So here we see that within causal inference, we use this concept of treatment in a very flexible way. Now the treatment is whether Stephen Curry shoots or whether the other player shoots, whether Courtney Lee shoots. So now we can interpret the statistics that we observed before in terms of these random variables. The 3-point percentage of Stephen Curry is the probability that a shot is made if Curry is the shooter. The 3-point percentage of Courtney Lee is the probability that the outcome is equal to 1. 3-point shot is made, given that the treatment is Lee. Lee is the one taking the shot. And again, we're going to explore whether these statistics can be interpreted causally. Now let's go to the third example, the grades in the Portuguese school. In this case, the outcome y are grades which have numerical values. They're no longer 0 or 1 as in the two previous examples. The treatment still is binary, still has two possible values, whether the student receives private classes, in that case t is equal to 1, or they don't, in that case t is equal to 0. Now the statistics that we explained before are no longer conditional probabilities, they are conditional averages. So we consider the conditional mean or the conditional average given the treatment, and we compute the average treatment effect, and we will see in a moment how. So here we see the two conditional averages. These are the conditional averages of the grades when t is equal to 1. Remember our notation for the conditional mean. This is the conditional mean of y given t when t is equal to 1, and this is the conditional mean of y given t when t is equal to 0. When we condition on 0, that's the average grade for the people that did not receive private classes, and it's 9.98. And now the average treatment effect is obtained by subtracting the conditional average when the treatment is 1 and the conditional average when the treatment is 0, and this is the observed average treatment effect in this case. And again, we will see whether we can interpret it causally. Finally, when we're considering unemployment in Spain, the outcome is the unemployment and the treatment is the temperature. Neither of these quantities are binary, so we're going to focus on the linear effect of the treatment on the outcome. So that is captured by the correlation between them, which happens to be minus 0.21. Equivalently, we can also fit a linear regression model of the outcome given the treatment and look at the coefficient, the linear coefficient corresponding to the treatment. In this case, the linear coefficient is minus 0.01. This might seem small, but this is just an artifact of the fact that temperature is measured in degrees Fahrenheit, where the order of magnitude is between like 50 and 80, whereas unemployment is measured in millions, which are much smaller. If we were to standardize both quantities, then the coefficient would be equal to the correlation coefficient, which is minus 0.21, which is pretty substantial. And now the question is, can we interpret both the correlation and the linear coefficient as a causal effect of temperature on unemployment. All right, so this is a very important slide because we're finally going to introduce the concept of potential outcomes, which enable us to talk about causal inference formally. Basically, potential outcomes define alternative scenarios that are tied to different values of the treatment. The way I think about it is as if these were hypothetical worlds where the treatment has just one value. They are always defined regardless of the actual value of the treatment. We will see what I mean in a moment with the examples. So here is the example of the new drug. The potential outcome associated to 0 basically is the outcome if the patient is untreated. Okay, so this indicated here, the patient was not treated and they recovered. In that case, that potential outcome is equal to 1 because they recovered. And here the 0 refers to the fact that they were not treated. Okay, so in these two cases, the patient was not treated. On the left, they recovered. On the right, they did not recover. We have a different potential outcome associated to the case where the patient is treated. So realize that now this is a 1 because the patient was treated, and this is a 1 because the patient was treated. And if the patient recovers in that case, the potential outcome is equal to 1. If they don't recover, the potential outcome is equal to 0. And the important thing to remember is that this is always defined for all patients, regardless whether they receive the treatment or not. It's as if we had access to two separate realities, one in which everyone received treatment and another reality in which nobody received treatment. And if we were able to have access to those two realities, then we can easily determine whether the medicine works or not, right? We go to the reality where no one is treated and we see how many people recovered, what fraction of people recovered. And then we go to the reality where everyone was treated and we see how many people, what fraction of people recovered in that case, and we compare them. So in that, that would make causal inference very easy. We'll see in a moment why it is not easy at all. With 3-point shooting, same thing. The potential outcomes represent situations in which only one of the values of the treatment would occur. The potential outcome associated to Curry is the outcome if Curry shoots for all possible shots, regardless whether Curry or Lee actually took that shot. It's equal to 1 if the shot was made and 0 if the shot was missed when Curry was taking that shot. And again, a lot of this, as we will see in a moment, is hypothetical. The other potential outcome is the outcome associated to Lee. If Lee shoots, it's equal to 1 if the shot is made, 0 if the shot is missed. Importantly, these two possible potential outcomes are defined for every shot, regardless of who shoots the shot. And now let's talk about this reality analogy another time, because I think it's quite useful. If you had access to a reality where Curry was taking all the shots and another reality where Lee was taking all the shots, then it would be easy to know who is the best 3-point shooter, because we would just go to the reality where Curry is taking all the shots and see what fraction of shots he's making, and then we would go to the reality where Lee is taking all the shots and we would see what fraction of the shots he's making, and we just compare. And that would enable us to immediately determine the causal effect. What about grades in the Portuguese school? Well, same thing. Now the potential outcome is not going to have binary values because it's a grade, but still there's going to be two potential outcomes which are going to be defined depending on whether we consider there's private classes or not. If there are no private classes, this is the potential outcome related to 0. If there are private classes, this is the potential outcome related to 1. Again, it's as if we had a reality where everyone was receiving private classes and another reality where no one was receiving private classes, and then we can compute the causal average treatment effect by just comparing the mean of the grades in the alternative reality where everyone is taking private classes with the mean of the grades in the alternative reality where nobody is taking private classes. What about unemployment in Spain? Now the treatment is not binary anymore, so we have a lot of alternative realities. Okay, we have a lot of potential outcomes that are associated with every possible value of the temperature. It is defined again regardless of the actual temperature that happened. These are just alternative realities that tell us what the unemployment would be for different temperatures. And if that is the case, then we can check the causal linear effect by seeing if the mean of the potential outcome associated with the different temperatures is linearly related to the value of the temperatures. Okay, now this coefficient in that case would tell us if there's a causal linear effect of temperature on the outcome on unemployment. What is so from the last 4 slides, it might seem as if causal inference is a trivial problem, right? We compute these 2 quantities that I mentioned in each of the cases. In the last one, we compute this linear coefficient. Boom, we're done. We know whether there's a causal effect. Unfortunately, that is completely impossible because we do not have access to these alternative realities. The potential outcomes, these alternative realities, are defined regardless of the treatment value. The problem is that we don't observe them in our data. We're only going to observe the one that is associated with the observed treatment. For example, if treatment is 1, in the case of the drug, if the patient receives the drug, we will observe what happens when they receive the drug. In this case, they recovered. We will have no idea what would have happened if they didn't receive the drug. We will just not know. And that is the fundamental problem of causal inference. We have highly incomplete information. All other potential outcomes that are not associated with the observed treatment are unobserved counterfactuals because they are counter to factual reality. They are not observed. So here the key question is, when do the observed statistics based on the data that we actually get to see, when do they reflect causal effects? When can we say that the fraction of people that didn't recover in this alternative reality where nobody received treatment is equal to the actual fraction of people that recover in the control group in our data? When can we say that the fraction of people that recover in the alternative reality where everyone receives the medicine is the same as the fraction of patients that recover in the treatment group? In the case of non-binary outcomes like the grade example, when can we say that the average grade in the alternative reality where nobody is receiving private classes is the same as the average grade for the students that did not receive private classes? When is the average grade in the alternative reality where everyone receives private classes the same as the average grade for the students that did receive private classes in reality? I use reality too much, okay? Sorry about that. Finally, when we have non-binary outcomes and treatment and we're interested in linear effects, when can we say that this true linear effect that we see when we have access to all of these alternative realities when there were different temperatures and we could have access to the corresponding unemployment, when is that equal to the observed covariance or the observed linear regression coefficient between unemployment and temperature? And there's a clear answer for this. All of these equalities are true if the treatment and the potential outcomes are independent. When are the treatment and the potential outcomes guaranteed to be independent? We're typically only under one condition: when we have randomized the treatment. We have chosen the treatment without looking at the patients, without looking at the students, without looking at anything else. We just produce a random treatment. In that case, we can aggregate our data in these ways through conditional probabilities, conditional averages, or with linear models or correlation to reflect causal effects. Let's illustrate why independence between the treatment and the potential outcomes is completely essential. Here is an example where, if you realize, like here I've the data that we get to observe is in here in color, and the data that, the potential outcomes that we do not get to observe are in light gray, so that you can still see what they are, but this represents that we don't actually get to see them, okay? And in this situation, you can realize each of these boxes corresponds to a patient. You realize that the patients that we're going to recover anyways, okay, regardless of the medicine. And the patients that were not going to recover anyways, regardless of the medicine. And now up here you can see whether they were given the medicine or not, and you can see that we're giving the medicine more often to people that were going to recover anyway. And this can easily happen. We'll go into details as to why a little bit later. And when we look at the control group of people that are not receiving the medicine, there's more people that were not going to recover anyways. Because of that, when we look at the control group and the treatment group, there's more people that recover in the treatment group and less people that recover in the control group, but that's just because of who we chose to give the medicine. We chose to give the medicine to healthier people. So there's no causal effect, and I know that because we're seeing the potential outcomes here, but because there is no independence between the treatment and the potential outcomes, there's a systematic difference between the control group and the treatment group, which makes it seem as if there is an effect when there is none. This is why independence is absolutely essential, independence between the treatment and the potential outcomes. Let's take a look at another example when we have a continuous treatment, like in our unemployment and temperature case. Here, again, we have access to the potential outcomes because this is a made-up example. They're all here. So all the potential outcomes here are exactly the same. This means that the treatment doesn't matter. We get to observe this guy here, but if the treatment had been different, if the treatment had been this, we would have observed the same value. Okay, and you see that this happens in these three data points. Like in this other data point, we saw this value of the potential outcomes, but because of other factors, here the potential outcome is higher and the treatment still has no effect. If we had chosen other treatments, we would have observed exactly the same outcome. And the same here, except that the potential outcome is lower, but you can see again that the treatment has no effect. So what's the problem? The problem is that are we choosing the treatment to be independent from the potential outcomes? Maybe take a little look and think about it. Well, definitely not, right? Because when the potential outcome is low, we're choosing a smaller treatment, and when the potential outcome is large, we're choosing a larger treatment, so that when we actually look at the data that we observe, it seems like the observed outcome is proportional to the treatment, that this is only because of how we chose the treatment. If you randomize the treatment, this would no longer happen, because it's very unlikely that you will only choose small treatments when the potential outcome is low and large treatments when the potential outcome is large. That's just not going to happen, or it will happen with such low probability that we don't need to worry about it. So this again is another example why independence between the potential outcomes and the treatment is absolutely essential so that we don't have situations like this where there's an observed correlation between the observed outcome and the treatment, which does not reflect causality. Now let's dig into this a little bit deeper by defining confounding factors. Confounding factors or confounders are quantities that induce dependence between the treatment and the potential outcome, which, as we've seen, is problematic to perform causal inference. Here we're going to study a situation where if we condition on the confounder, then the treatment and the potential outcomes are conditionally independent. So in that case, if we fix the value of the confounder, we only consider data points for which the confounder has a fixed value, then it's as if we had a mini randomized trial for those values. Conditioned on that value of the confounder, the treatment and the potential outcomes are going to be conditionally independent, which means that in that subgroup of data, we can perform causal inference using observed statistics. This assumption essentially says that the confounder completely governs dependence. There's no additional confounders. All right, so let's take a look at what happens when there's a binary outcome and a binary treatment under this assumption. We're going to consider a confounder that has C values. We can write the observed conditional probability that we're interested in of the observed outcome given the treatment being equal to 1 as this weighted sum of the conditional probability of the potential outcome given the confounder. This is because of the conditional independence assumption. You have many more details in the specific video on causal inference, potential outcomes and confounders for binary outcomes and treatment. And the problem is that it is going to be weighted by the conditional probability of the confounder given the treatment. If you think of our control and treatment group, this is the fraction of people that have each of the values of the confounder within the treatment group. And when that is not the same as the fraction of people that have that value of the confounder in the whole population, that's when these probabilities get distorted. Because the probability that we're actually interested in, the probability in this alternative reality where everyone would receive the treatment, the probability that the potential outcome associated with 1 is 1, is equal to exactly the same sum, except that now these guys are weighted by the probability, the fraction, or the probability of each value of the confounder, but over the whole population. And if that is different to how frequent that value of the confounder is in the treatment group, then that's going to distort the observed effects. Let's take a look at a concrete example. Age often acts as a confounder when we're evaluating drugs because young people might be more or less prone to taking certain medicines than old people. In our example here, we have that young people that are up here always recover, regardless whether they receive the treatment or not. They always recover. That's why they're all so happy. Whereas here, old people sometimes recover if they received the drug. So here you see that for this particular person, the potential outcome associated with not receiving the drug is not recovering. The potential outcome associated with receiving the drug is to recover, but some of them don't, okay? Half of them actually recover, half of them don't when they take the medicine. Now, because we're not doing a randomized trial, we're just allowing whoever wants to take the medicine, it turns out that the young people take the medicine more often and the old people take the medicine less often. Okay, so you can see here that there's just 2 ticks down here and there's many ticks up there. So what's the problem with that? The problem with that is that when we build our control, so now of course we only get to see the data determined by the treatment, right? Like all the rest are counterfactuals that boom, disappear. And now when we aggregate all of this to build our control group and our treatment group, what is going to happen? We're going to get more young people in the treatment group, which are overrepresented in the treatment group with respect to the whole population. In the whole population, we have this, in this example, half of the people are young and half of the people are old. And old people are going to be overrepresented in the control group. But what's the problem here? Young people recover regardless. So this is going to boost the probability of recovery in the treatment group artificially just because of how we have chosen the composition of the treatment group. So you can see here why this confounding factor would artificially inflate the probability of recovery in the treatment group and deflate, again artificially, not reflected to causality, the probability of recovering in the control group. What about the example with Stephen Curry and Kearney Lee? So it is true that Kearney Lee had a higher 3-point percentage than Stephen Curry, but is there some possible confounder? Maybe think about it. You might have come up with the difficulty of the shots because obviously the defense is going to focus much more on Stephen Curry, which at that point was perhaps the top player in the NBA, rather than on Kearney Lee. That is kind of difficult to quantify, so instead we can take a look at shot distance. If we look at shot distance, we can see that Stephen Curry actually shot better in short threes that were close to the 3-point line. he shot 50%, while Courtney Lee only shot 48.3%. Now let's take a look at what happened for longer threes beyond 24 feet. Well, there Stephen Curry shot much better, 39.6%. Compared to 34.5%. So this is very strange, right? When we only consider short threes, Curry shoots better. When we only consider long threes, Curry shoots better. But overall, Lee shoots better. That phenomenon is known as Simpson's paradox. And the way we can explain it, actually, maybe I would encourage you to take a look at the data and see if you can explain it by yourself. You stop the video because I'm going to tell you the answer right now. The answer is that if you look at the percentage of Curry's shots that were taken from close, it's just around 20%, whereas for Lee, it's almost 68%. And we see that for both players, those shots are much easier. And for both players, long threes are much more difficult. So this is just about shot selection. Courtney Lee can shoot many, many more short threes, probably because the defense is not so focused on him, whereas Curry has to shoot many longer threes that have lower percentage. And this distorts the observed statistics so that we might be fooled into thinking that Courtney Lee was the better shooter. Finally, we have two examples left, We have the example with the non-binary outcome but binary treatment where we have grades, so we consider the conditional averages of the grades given whether people received private classes or not. And then we will talk about the unemployment and temperature. So for a case where we have binary treatment and non-binary outcome, we're interested in when this conditional mean given that the treatment is 1 is equal to the mean in this alternative reality where everyone received the treatment, where everyone received private classes in our example. And again, this is distorted by the fraction of each value of the confounding factor within the treatment group, because that's what weighs the conditional means given each value of the confounder to yield this observed statistic under the conditional independence assumption that we mentioned earlier. And the problem is that when we actually look at the mean of the potential outcome that we're interested in, by the law of total probability, it's equal to the weighted conditional averages, but we weight by the fraction of that value of the confounder in the whole population, not only in the treatment group. And that can be systematically different, which will distort the observed effects. Let's take a look at the example with the grades in the Portuguese school. A possible confounder here is whether students previously failed the course or not, which might reflect that they are weaker students. So if we look at the conditional mean function given both the confounder and the treatment, if we look at students that previously failed, whether they receive private classes or not, their grades are relatively low. And for these students, at least, it seems that the private classes kind of helped, okay, because their grades are a bit higher when they receive private classes compared to when they did not receive private classes. But surprisingly, if we look at the students that did not previously fail, the private classes are useless. Why did I say surprisingly? This is because when we actually look at who is taking these private classes, the previously failed students are more likely to not take private classes. So I got confused there for a moment. This is what I mean. If we look at the fraction of previously failed students within the treatment group, that's 12%. And if we look at the fraction of previously failed students within the control group, it's almost 29%. So among the students that took private classes, the previously failed students are underrepresented, even though for those students, private classes seem to be effective, whereas students that did not previously fail are overrepresented in the treatment group, even though for them, the private classes seem to be useless. That's what I meant. Sorry that I got a little bit confused there. And now what happens? Well, it seems that in the group that received private classes, systematically there's less of these students that previously failed, and that is artificially going to make the treatment group look better. The average, the grade average in the treatment group is going to be artificially higher because it does not include as many of these students that previously failed. Now let's consider the case where we have a non-binary outcome and a non-binary treatment. This is the example with weather and unemployment. If we assume a linear model given the confounder and the treatment, where the potential outcome in this alternative reality where t is equal to a certain fixed treatment value, basically the potential outcome is a linear function of that treatment value, but also of a confounder and some other quantity that is just independent. Okay, it says independent from T and C, so we will see that it doesn't really matter. When we actually look at the observed values, now they're going to depend on the observed treatment, but also on the confounder. So what happens when we compute compute a short linear regression model of the outcome given the treatment? We will see in a moment why we call this a short linear regression model. Then the coefficient, if everything is standardized, is equal to the covariance between the outcome and the treatment, and that covariance is also going to capture the effect of the confounder in the following way. It's going to be equal to the true causal coefficient that we're after, plus a quantity that is equal to the covariance between the treatment and the confounder times the coefficient of the confounder. So if the treatment and the confounder are independent because the treatment has been randomized, that's going to be 0, no problem. But if it's not, that effect of the confounder on the outcome is going to contaminate the linear coefficient that we observe. In unemployment and temperature in Spain, we observe this negative correlation between unemployment and temperature. What could be a possible confounder? Well, a possible confounder would be the number of tourists that arrive in Spain, because tourists tend to come to Spain when it's warmer, and when there are tourists, there are more jobs, so indeed the unemployment is lower. When the temperature is lower, there are no tourists, and the unemployment is higher because there are less jobs. It's not that there are less tourists, so less jobs from the tourism sector, and this is reflected in the unemployment. Okay, so now we're going to see how to adjust for confounders when we know about them. And here the motivation is that randomization is absolutely awesome because it manages to neutralize every possible confounder, even if we don't know about them. So it's just amazing. But it can actually be very costly. Randomized controlled trials for medicine, for drugs, are extremely costly. And sometimes it's just not even possible. So think about our shooting example. We cannot go to the NBA and say, hey, look, now we're going to randomize who takes this shot. For example, Stephen Curry and Corneli didn't even play for the same team. So, forget about randomizing. You just have to work with the data that you have. Same thing for unemployment and temperature. We cannot randomize the temperature in Spain. Of course, you can look for situations where the treatment is randomized for some other reason. And in economics, I was looking for economists. That's the word I was looking for. Economists often do this, but these are very specific situations. Okay, in many situations, we just do not have access to randomized treatments. Because of that, it is very useful to be able to correct at least for known confounders, because that will improve our causal interpretation of the observed statistics, even if it will not guarantee that the effects are truly causal. We're going to assume that the treatment is conditionally independent of the potential outcomes given the observed confounders. In that case, we're going to show that you can actually do this. How do we adjust for a confounder? If this conditionally independent conditionally independent assumption actually holds, remember that I said that that's kind of saying that for each specific value of the confounder, it's as if we had a randomized trial. Okay, because we do have this conditional independence between the potential outcomes given the confounder. this conditional independence between the potential outcomes and the treatment given the confounder for each specific value of the confounder. In that case, the conditional statistics given the confounder are okay. They actually reflect causal effects. What we need to do is we have to be careful about how we combine them to make sure that we estimate the true causal effect. We're going to see how to do that for each of our examples. So in the case of the new drug, our problem was that young subjects or young patients were overrepresented in the treatment group and underrepresented in the control group. But if we only consider young patients, that's not a problem, because we can just take the treatment group and see, okay, what fraction of young patients recovered, and we can just take the control group and see what fraction of patients recover, and we discover the true conditional causal effect, which is that they recover regardless. And we can do the same for the old patients. Now they're not mixed in with the young patients, so we're not going to get confused because of the overrepresentation of old patients in the control group. We just look at the control group and realize that none of them recover, so we estimate the true causal effect when they don't take the medicine, which is none of them will recover. And we see that half of them recover when they take the medicine, and now we don't care that there's more of them in the control group and less of them in the treatment group because they're not being mixed with the young patients. This allows us to estimate the true conditional causal effects given the confounder, which is age. And now we just need to combine these two conditional effects, and we have to be careful. We have to combine them using the actual fraction of young people and old people in the population instead of the fraction of young people and old people in the treatment and control groups, which is what was happening before. If we do that, we actually get to observe the true causal effects. And if we looked at the old causal effects, we see that because old patients were overrepresented in the control group, we were underestimating the probability of recovery if you don't take the medicine, and because younger patients were overrepresented in the treatment group, we're overestimating the probability of recovery if you take the medicine. And this can be, again, corrected for by stratifying, which means separating the old patients and the young patients. What about 3-point shooting? Where, same thing again, we can look at the probability of making a shot given that you're shooting a short 3 or given that you're shooting a long 3. And the key is to combine these guys using the same probability of shooting a short 3 and the same probability of shooting a long 3. So here what we're saying is, imagine that Curry and Lee were shooting the same proportions of short and long 3s. Here the proportion, basically what I did was I combined all of their shots. You could also have just looked at the whole of the NBA. How often do players shoot a short 3 and how often they shoot a long 3? And when you combine these conditional probabilities in that way, then this clearly reveals that Curry is a much better shooter than Lee. And this was not revealed at all in the original statistics because Curry shoots many more longer 3s that are more difficult, and Lee shoots many more shorter 3s that are easier for any player. By using the same probability of a short 3 or of a long 3 for both players, we control for this confounder, which reveals that Curry is the better shooter. Now for the grades in the Portuguese school, again, we had this issue where the students that previously failed were overrepresented in the control group, and we can control for that by using the percentage of students that previously failed over the whole population and multiplying that by the corresponding observed conditional average, which do reflect the true conditional causal effects under our assumption. So here our assumption is probably not true at all because there's many other possible effects, but still we can control for the presence of previously failed students, which is different in the control group and the treatment group, by combining the conditional averages in this way. And this shows that in that case the private classes have a smaller effect than originally. It's interesting because originally this observed effect was driven precisely by the students that did not previously fail, for whom it seems that the classes were useless, but there were just more of them taking the classes, and because they typically get better grades, that was inflating the conditional average for students that took classes. And now that we have corrected for that, once we have corrected for that, the average treatment effect is actually driven by the other students, the students that previously failed, because for them it does seem that the classes seem to help as long as there are no other confounding factors. And finally, let's take a look at the non-binary outcome, non-binary treatment case, where we're assuming a linear model where there's a linear relationship between the outcome and the treatment, and also between the outcome and this other confounder. And the way we can adjust for it is, again, taking it into account, if you want, conditioning on it in a way by including it in the model. So previously we were fitting a linear regression model where we were fitting the response as a function of the treatment. Now what we do is we fit the response as a function of the treatment and also the confounder. This is why before I was referring to the other treatment model, the other regression model as a short regression, because it only had one feature, the treatment. Now this is a long regression which has two features, the treatment and the confounder. In that case, under these assumptions, we are guaranteed that we are going to find the true causal coefficient associated with the treatment, because the feature representing the confounder is going to absorb the effect of the confounder. It will no longer be put into the coefficient related to the treatment, as happens in short regression. So in our example, we want to incorporate tourists. So now we're showing unemployment color-coded in this way as a function of both temperature and tourists. And now we fit a linear model where the features are both temperature and tourists. And when we do that, suddenly the coefficient corresponding to the temperature becomes extremely tiny, and it's actually positive. So this conclusively shows that temperature does not have a causal effect on unemployment, of course, assuming that there are no additional confounders, and this, is consistent with common sense. It's the tourists that were governing this dependence between temperature and unemployment, acting as a confounding factor. Without the confounder, remember that we did have a strong coefficient. This is a strong coefficient because if we standardized, it would be equal to minus 0.21 between the temperature and the unemployment, which would fool us into thinking that maybe next month, if suddenly the temperatures would go up, the unemployment would go down, which is of course nonsense. Okay, so what have we learned? We have learned that observed statistics do not necessarily reflect causal effects. They do if the treatment and the potential outcomes are independent, which can be achieved by randomizing the treatment. Otherwise, confounders can completely distort observed effects in conditional probabilities, conditional averages, correlation, or linear models. And we can adjust for these confounders as long as they are known and as long as we assume that the treatment and the potential outcomes are conditionally independent given the confounders. And that's all I got. Thank you very much.